Okay, welcome back. The next speaker is Benjamin Linowitz, and he will be talking about the systolic geometry of arithmetic locally symmetric spaces. So please.
Thank you. It's a pleasure to be here. I'd like to thank the organizers for the invitation. So the goal of my talk is, I suppose, twofold. Of course, I want to talk about a result that's joint with my collaborators, Sarah Lepan and Jeff Meyer. I also want to provide a very friendly introduction to systolic geometry. And so I'm not going to assume that you know anything about it. Maybe the result that I have with Sarah and Jeff is an application of arithmetic group theory to systolic geometry. And so I want to convince you that this area, systolic geometry, is a living, breathing area of geometry that people care about and that wasn't invented so that arithmetic groups, people like me, have somewhere to apply our results to. So the systole of a compact Riemannian manifold is the least length of a non-contractible geodesic loop. So it's very easy to construct manifolds with arbitrarily small systoles. For surfaces, you've seen like a genus 2 surface. Imagine pinching that middle part between the two holes, so it gets very tiny. So then for such a kind of dumbbell-shaped surface, you have a small systole. On the other hand, it's also very easy to construct manifolds with arbitrarily large systoles. So we've been talking a lot about manifolds you get from central simple algebras. Imagine you want to construct a surface with a very large systole. Well, arithmetic surfaces come from quaternion algebras. Geodesics on arithmetic surfaces come from embedded maximal subfields. If you don't want any short geodesics, you don't want any maximal subfields, any quadratic fields that could give rise to a short geodesic to embed into your quaternion algebra. How do you arrange this? Well, there's only going to be finitely many quote unquote bad quadratic fields. For each of them, take a prime that splits in that field and make your algebra ramify at that prime. There is going to exist a quaternion algebra associated to these ramified primes. The lattices you get from this algebra are going to have large systole. The issue is that naive constructions like this yield manifolds with enormous volumes. For instance, in the construction I just told you, well, by the volume formula, there's going to be a factor, the norm of each of those primes that's ramifying. And even if you use some sort of GRH-dependent effective form of the Chebyshev density theorem, it's still going to be huge. So something I learned in making this talk is if you Google the term systole and you don't include topology or something like that, this is the picture that you get. So the idea is that their heart has two phases. It has a diastole phase, that's when the heart's filling up with blood, and it has a systole phase, when it's contracting and spreading the blood throughout the body. So in, I think, 2005, Marcel Berger wrote the notices of the AMS as one of these "What is a" series of articles. The medical term systole comes from the Greek word for contraction. If you have extra systolic beats in the medical and not geometric sense, you better consult your cardiologist. The mathematical term systole was coined in 1980. So Berger is being a little bit modest here. He knows it was coined in 1980 because he was actually the one who coined it. And in a later interview, I guess, he went into the details. So this, it's kind of long, but it's very, very interesting. So I was looking at the time for a word of the type iso something ic, both for systoles and for the injectivity radius. I looked at Greek language dictionaries and found various wordings. Luckily, I was doing physical education together with a Greek literature colleague. He told me what I was proposing was low Greek. I explained to him in ordinary words what a systole and the injectivity radius are. At the next week's physical education session, he came back with two proposals, isoclysteric and isosphincteric. So a clister is a sort of old-timey word. It means enema. So I was still young in the bad sense, to say provocative, and I was amused. But I told these two wordings to the best seminar that week. So the best seminar, I was talking to Yves about it the other day, and then I got really interested in it. So Arith-Metic was a pseudonymic group of French differential geometers led by Berger, sort of like Nicolas Bourbaki. So Bourbaki, the name Bourbaki comes from a general of Napoleon. So the name Arith-Metic, who's published several books, well, Besse is a town in the middle of France where the first workshop was held. Arthur is after King Arthur, like Knights of the Round Table. So anyhow, these French differential geometers of the Round Table were horrified and told me, Marcel, you cannot use that. So at the next session, I asked him to find less bad taste ick words. The following week, he came back with isosystolic and isoembolic. The seminar people were happy. You understand that in short, I switched from proctology to cardiology. So we were that close to studying, sphincters of manifolds, rather. All right. So the first big result in systolic geometry was in 1949 by Charles Lohner. He proved that if you have a two-dimensional Riemannian torus, its systole is less than a constant, which is explicit, times the square root of its area. And so technically, a student of Lohner's, I think his name was Pu, about 2 years earlier, defined systole, but for metric graphs. I think in graph theory, maybe it's called the girth of the graph. But this was the first big geometric systole result. But like I said, he wouldn't have used the word systole since it wasn't coined for another quarter of a century. A few years later, Besekovich proved that if you have an oriented Riemann surface, an oriented surface with genus at least 1, the systole is less than √2 times the square root of the area. So in 1961, Berger was telling René Thom about these systolic inequalities and maybe half a dozen other ones that were similar, that were proven in the 40s and 50s. And Thom's reaction was, mais c'est fondamental. These are of fundamental importance. The reason, I suppose, is that geometric invariants are just inherently interesting. If you have an inequality relating several of them, that's doubly interesting. If you can prove your inequality is optimal, best possible, that's especially interesting. Apparently, this conversation really motivated Berger, who probably more than anyone would go on to popularize systoles and these systole inequalities. So the next really big result came in 1983 when Gromov published his Filling Riemannian Manifolds article. He proved if you have a closed aspherical N manifold, there's a constant which depends only on dimension, such that the systole is less than that constant times the volume to the 1/n. So on the other hand, if you have something like a compact hyperbolic surface of finite area, you can obtain a much better estimate. You can obtain an upper bound of the form, the systole is less than twice log of the genus. And so I'll show you just the general idea where this logarithm comes from. So take your surface, take a point on it, take a little disk centered at that point. I don't know. Let's say its radius is r. All right, start expanding the radius. So eventually, the disk has to intersect itself. The idea is the disk has some finite area that's growing with the radius, and our whole surface, whose area has to be bigger than that of the disk, well, has finite area. So here's the thing, the area of the disk is approximately pi times e to the r. So here's what's going to happen. The moment our disk intersects itself, you get a non-contractible closed loop whose length is going to be less than twice the radius. All right. And so you're going to get something like the length of our geodesic is less than twice the radius. Now, that is going to be approximately twice the logarithm of the area here, which is less than the area of the entire disk, of the entire surface, excuse me. Then you just convert it into genus. So what the area of the surface is like 4 pi g minus 1. And so that's where the logarithm here comes from. And what I want to emphasize is this argument that gives you logarithm of the area has nothing to do with surfaces. As long as the volume of a unit ball is going to be exponential in the radius, this same sort of argument is going to work. All right. So the first result I want to talk about, so this is due to Boozer and Sarnak, a paper in 1994. In case you're curious, this is the paper where they prove that with only finitely many exceptions, every lattice in SL2R has a non-congruent subgroup with index at most 2. But here's the result about systoles. There exists hyperbolic surfaces S such that for every prime P, the congruence cover has systole bigger than 4/3 log of the genus minus some constant. So, towards the end of the talk, I'm going to give you the actual proof of this. And maybe what I want to emphasize now is the proof of this is very straightforward. I mean, it's very clever, but it really doesn't amount to much more than take this very simple quaternion algebra. You don't need to know anything about algebraic number theory. It's defined over Q. Take this lattice inside of it, embed it in SL2R, take a congruent subgroup. Almost by definition of congruent subgroups, traces in a congruent subgroup have to be big. The trace is related to the length of a geodesic. So the first time I looked at this argument, I thought, well, there's nothing sort of remotely exotic about this. This is a very natural, if you were an arithmetic lattice person looking for families of surfaces with large systole, congruence covers is probably one of the first things you would look at. So I was surprised when I saw this. The surfaces of Boozer and Sarnak are among the strangest and most interesting examples in Ramanujan geometry. So this is from Larry Guth's article, Metaphors in Systolic Geometry. It's from the proceedings of the ICM in Hyderabad in 2010. And so at first I was sort of confused about this because in my mind, I mean, you took a very simple quaternion lattice, you take a congruence cover, there's nothing sort of strange about it at all. And then it sort of occurred to me, oh, well, if you're a geometer used to doing like classical low dimensional topology, classical surface theory result techniques, it's extremely difficult to produce surfaces with systoles this big. It really does require this kind of magical arithmetic input. And I don't know how the ICM works in this sense. There are two versions of this paper. There's the official version, and then there's the version that Guth put on the archive, which is considerably longer. And Guth actually has, it's probably like 3 pages devoted to arithmetic lattices and why he's so fascinated by them. And something that really struck me was the following. Arithmetic hyperbolic surfaces are remarkably hard to picture. When I meet a mathematician who studies the geometry of surfaces, I often ask them if they have any ideas about visualizing arithmetic hyperbolic surfaces. They just laugh. Part of the problem is that the systole of an arithmetic hyperbolic surface is only about log of the genus. That means to get interesting behavior, we need to look at huge values of G. Naturally, it's not easy to imagine a surface of genus 10 to the 6th. And so I think in the last talk and several talks yesterday, Vigneron's examples of isospectral surfaces were mentioned. And so think about those. As an arithmetic person, these are extremely simple. The quaternion algebra is defined over Q adjoin root 10. And so very concrete. So to define a quaternion algebra, you need to define the primes that ramify in it. There's an infinite prime, and then the primes are like 3, 11, and something else. I think, again, very explicit. Nowadays, if you use Magma will actually spit out like matrix representatives for the elements in these fundamental groups of hers. Magma will give you presentations. And so on the one hand, this is very explicit, very concrete. On the other hand, if you work out the genus of her examples, I haven't done that, it was a decade ago I did this, it was like 30,000 or 100,000 or something that's so large that if you're looking for visual inspiration, visual insight, it's probably no better as an example than just an abstract existence proof. And so, I don't know, I recommend that you look at this paper of Larry Goots. It's very interesting, his comments about arithmetic lattices. So I want to say that any family of surfaces has large systole if their constants gamma and c. So gamma is going to be the multiplicative constant, c is the additive constant, such that the systole is bigger than gamma log genus. So Boozer and Sarnak's work shows that principal congruence covers of certain surfaces have large systoles. So Boozer and Sarnak's constant was 4/3. On the other hand, our naive bound over here gave us a 2. That means the best possible bound is between 4/3 and 2. So a theorem of Makasumi, this was actually his undergraduate thesis at Princeton, that for principal congruence covers of a hyperbolic surface, the best possible multiplicative constant is in fact 4/3. And so these surfaces of Boozer and Sarnak do realize the optimal bound. Okay, in 2007, Misha Katz, Mary Shaps, and Uzi Vishne proved that if S is any compact arithmetic hyperbolic surface, then there's some constant depending only on the surface, such that congruence covers satisfy the same systole inequality. And moreover, they prove an analogous result for 3 manifolds with a constant of 2/3. And so now we know that this Boozer-Sarnak construction works for any arithmetic compact hyperbolic surface. And again, the hard work in the proof of their theorem is to get trace estimates for elements and congruent subgroups. So in 2016, I think this is one of the results from his PhD thesis. You could ask him yourself. I think he's one of the speakers later this week, Plinio Murillo. He proved if M is a Hilbert modular variety of dimension 2n, then the systoles of principal congruence coverings satisfied that they're bigger than 4/3√n log of the volume. So now we have 2 manifolds, 3 manifolds, Hilbert modular varieties, arithmetic hyperbolic manifolds of the first type. Now it's 8/nn+1 log volume. And in an appendix with Kyodoria, he proves that this bound, multiplicative constant, is best possible. So here's the result I proved with Sarah Lepam and Jeff Meyer, that all of this holds for arithmetic simple locally symmetric spaces. So in particular, All of these previous results hold for finite volume, real, complex, and quaternionic arithmetic hyperbolic manifolds. So in order to describe our proof and what goes into it, I want to give you the Boozer-Sarnak proof. And like I said, it's very, it requires no sort of big technicalities. It's very self-contained. There's, no references to work of Langland's or anything like that in it. And here's what happens. A is a quaternion division algebra over Q. It's going to have basis 1, I, j, k. I squared is little a, j squared is little b, ij is k, and that's negative ji. Little a and little b are going to be positive integers. You have to choose them so that you get a division algebra. This isn't hard. In fact, there's a computer algebra system that will just do it for you. Okay, an arbitrary element in any quaternion algebra has this shape. In this case, it's over Q, a rational number plus x1i, x2j, x3k. Fantastic. Every quaternion algebra has a reduced norm. In this case, it's the following quadratic form: x0 squared minus ax1 squared minus bx2 squared plus ab x3 squared. So this is going to be our lattice. Take all elements in the quaternion algebra with integer coordinates whose norm is 1. So nothing fancy about this. This is kind of sort of analogous to, you're familiar with like the Lipschitz quaternions. So that's going to be our starting lattice. For an odd prime P, take its principal congruent subgroup, gamma P. Elements that are congruent to 1 mod P. So we can embed A into M2R, and it's totally explicit, this embedding. So it looks weird. Here's where this comes from, because I claim this isn't weird at all. Over the real numbers, there are precisely, up to isomorphism, 2 quaternion algebras, Hamilton's quaternions and M2R. If you have a quaternion algebra isomorphic to M2R, so its Hilbert symbol is like A, B, R, this is literally the isomorphism. So this is the map that gives you an isomorphism from extension of scalars from A to R to M to R. So that's the embedding that we're going to use. You can, I'm not going to make you can check the determinant of this matrix is the same as the reduced norm of the quaternion. So everything had reduced norm 1, which means gamma is going to land inside of SL2R. So we're going to get a lattice. We chose all of the entries in our quaternions to be integers so that we get a discrete group. So A is a division algebra, and gamma P is torsion-free. Therefore, what we have here, H2 mod gamma P, is a compact Riemann surface. Its genus is P, P minus 1, P plus 1, V plus 1. For some number V, which doesn't depend on P, I'll tell you where that comes from. So the genus is not multiplicative in covers, but the area is, right? So what's the degree of the cover this over H2 mod gamma? Well, gamma surjects onto SL2 Z mod PZ. Gamma P is the kernel. And so the degree of that cover is the cardinality of the group SL2 Z mod PZ. And so what's that cardinality? Well, the first column, you have P squared minus 1 choices. You can choose one entry in the other column arbitrarily. The final one is determined by the determinant 1 condition. And this is the degree of the cover. So if you actually just compute the genus upstairs, 2G minus 2 equals 2 little genus downstairs minus 2 times P, P minus 1, P plus 1. This is the formula you get. So again, very straightforward. What's the systole? Well, if we have something in gamma p and we look, well, then x is congruent to 1 mod p, which means p divides x3, x2, and x1. Okay, if p divides x1, then p squared divides x1 squared. P divides x2, p squared divides x2 squared, etc. So the reduced norm is 1. That means mod p, x naught squared is 1, so x naught is plus or minus 1 mod p squared. All right. So if x is not plus or minus the identity, then x naught can't be plus or minus 1. So the reason, if you go back to that matrix that I defined, its trace is 2 times x naught. If x naught was plus or minus 1, the matrix would have trace plus or minus 2. But that would mean that that matrix was a parabolic. But we don't have any parabolics inside of gamma. So that means that x naught has to be at least p squared minus 1. And so this, I don't know, it seems silly. This is somehow the whole crux of the argument, is x naught is congruent to plus or minus 1 mod p squared, but it's not equal to plus or minus 1. Therefore, its absolute value is at least p squared minus 1. The trace is twice x naught, so the absolute value of the trace is 2 p squared minus 1. The translation length of x, there's a formula for it involving hyperbolic cosine. It's hyperbolic cosine of the length over 2 is plus or minus trace over 2. If you put this trace estimate over here, and then you solve for the length, you get the systole is going to be bigger than twice log of p squared, which just, futzing around with logarithms of powers of p is 4/3 log of the genus. That's the Boozer-Sarnak construction. Are there any questions so far? Yeah. Yes. If you fix the prime, yeah, I don't think that this will work. I think you really do need, yeah. Okay, so the generalization. So I want to talk about how you can generalize this to really any arithmetic locally symmetric manifold. So here's the idea. I want to start with, I'm sure the name isn't going to take off and catch, but standard special linear manifolds. Just things that look like SLNR quotiented by SON, and gamma, where gamma is a torsion-free lattice you get from norm 1 elements in a maximal order in a central simple algebra. Sort of like the type of manifolds that have come up several times already related to the Lubatsky-Samuels-Vichny paper. So I want to call this a special linear manifold or orbifold. And I want to show you that you can essentially use the Boozer-Sarnak proof for these special linear manifolds. Bless you. Okay, so I'm going to take a central simple algebra over the rationals of dimension n squared. O is a maximal order. So given a natural number n, we have an ideal NO. The quotient O mod NO is a finite ring. We define the level n principal congruent subgroup as the kernel of the homomorphism from O1 to the units in O mod NO. Okay, fine so far. I'm going to call these O1, O1n, and I'm going to denote them gamma, gamma n, just like before. Okay, so here's our trace estimate. So let notation be as above. Take a prime P which doesn't ramify in A. All you have to know about central simple algebras for this is only finitely many primes ramify. So this isn't a big deal. And we want it to satisfy P is greater than 2n. then the statement is for every m that's at least 1 and semi-simple element x inside of gamma p to the m, x not the identity, there's an integer q such that q is less than n over 2 and the trace of x to the q is big. All right. So here's the proof. Choose bases so that locally everything is just matrices. Remember, P doesn't ramify, so locally we do get just the full matrix algebra. So phi of P is going to be the projection from Mn Zp, our maximal order, onto Mn Z mod P to the M. Well, the definition of a congruent subgroup is that it projects to the identity. The identity has trace n. Well, the n by n identity matrix is trace n, fine. So if you're an integer matrix that mod p to the m is the identity, it follows that your trace is congruent to n mod p to the m. All right, so this shows that if x is in our congruent subgroup, the trace of x is p to the mk plus n. So far, I don't know, modulo some jargon about central simple algebras, this is exactly the same. Now, before, I gave an argument about why can't the trace be equal to n? Well, if n is 2, we said, oh, well, there's no parabolics. Here's what we're going to do now. And this is why, notice this doesn't say the trace of x. It says there's a power of x. If the trace of every power of x is equal to n, then you can use the Newton identities to show that the characteristic polynomial of x is just x minus 1 to the n, and that x is the identity. But that's a contradiction to our hypothesis up here, and proves that the trace of some power of x is bigger than p to the m minus n. All right. So in the paper, we have these trace length bounds. I don't know. Frankly, it's probably the most interesting part of the paper, even though it's just a tool to prove our main theorem, or the least most useful. And here it is. If you have a semi-simple element x and SLNR, its translation length is bounded below by √2 inverse hyperbolic cosine trace over n. We also have an upper bound. I think maybe √2 is replaced by 2 in the upper bound. We don't need it here. And the idea was we wanted a result similar to the formula we get for SL2R, but we want it in SLN, and the actual formula for the translation length is much more complicated. So we got these bounds. In case, I don't know, it's your thing and you find these useful, we have a follow-up paper where we have good upper and lower bounds for the translation length in terms of log of the Mahler measure of the characteristic polynomial. Again, in analogy with the SL2R case. So the translation length is bigger than a constant arc hyperbolic cosine trace over n. Substitute this result into the last one, and we get the systole of our special linear manifold is bigger than 2√2 over n arc hyperbolic cosine p to the m minus n over n. We do a little algebra. We get a very, I want to stress how little effort we put into getting the best possible bound for this index. And we get something like this. So we get a lower bound for the systole of our special linear manifold, which is a constant, depending only on dimension, times log of the volume. Okay, so this gives us our result for special linear manifolds. What about more general spaces? So in this case, we make use of the following fact. Every arithmetic, simple, locally symmetric manifold is commensurable to an immersed, totally geodesic submanifold of a standard special linear manifold of explicitly bounded degree. So we're going to take the general case, immerse that manifold into one of our special linear manifolds, and then deduce the result from that. Now, all of our constants are going to depend on this bounding degree. And so I thought it was kind of silly if we had, this is supposed to be a geometric theorem. It's supposed to be of interest to topologists and people like that. I thought it would be silly if we had a constant which depends on all sorts of algebraic group terminology that a topologist might not know. And so what we did was we used Prasad's volume formula to take all of the terms in this bounding degree and just convert them into something involving the volume of the manifold. And so our ultimate result for the general case, the multiplicative constant depends in an explicit way on the volume of the base manifold. So this shows that for a broad class of arithmetic locally symmetric spaces, the systole is greater than a constant log of volume minus another constant. And so, like I said, we give explicit values for these constants. C1, the multiplicative guy, is going to depend on the volume of n in general, but when you have a real complex or quaternionic hyperbolic orbifold, there's no dependence on the volume. It just depends on dimension. It's totally explicit. And so, I mean, maybe it's my fault because I was the one who lobbied against it. We didn't really put any effort into getting the best possible bounds. We just got multiplicative constants. Shortly after our paper appeared on the archive, In-Kang Kim determined what he called optimal multiplicative constants for several important classes of arithmetic lattices, and he gave very good multiplicative constants in other cases. So here's his result. The multiplicative systole constant can be taken as follows. For lattices in SO1n, 4 over n plus 1. I'm sorry, this is supposed to be a comma. Yeah, that's nothing to do with the n plus 1. For lattices in SUN1 of the first type, C1 can be taken as 4 over nn plus 2. For the other type, 2 over nn plus 2. For lattices in SLn plus 1R, root 2 over nn plus 2. I need to, in a tactful way, there's something I don't quite understand about the paper. I suspect it's just a language thing. The introduction makes it sound like these are all optimal bounds. But in SL2R, so n equals 1, this gives you root 2 over 3. But I said the optimal bound in SL2R is 4/3. And Kim even writes this at the end of his paper, and he says the problem is with the trace length bounds he's using they're not as good in n equals 2 as they are in higher n. And so it isn't clear to me the extent to which any of these are optimal versus just very good multiplicative constants. All right. In 2022, so a couple years ago, Vincent Emery and Ken Kim and Plinio Murillo proved that the optimal multiplicative systole constant for compact quaternionic manifolds, dimension 4n, is 4 over n plus 1 to n plus 3. So here we can...
You mean quaternionic hyperbolic manifolds?
Yes.
Okay.
Quaternionic hyperbolic, thank you. So here we can do something to sort of check that all of these results are correct. So one-dimensional quaternionic hyperbolic space is isometric, four-dimensional real hyperbolic space. And at this point, we have optimal constants in both of them. So we can actually check 4 over 1 plus 1 times 2 plus 3 is equal to 8 over 4 plus 1. And in fact, these are both equal to 2/5. And so there aren't any contradictions. Okay, and so I just want to end, when this conference was supposed to take place 4 years ago, our paper had been accepted, and in the backlog of communications and analysis and geometry, I'm happy to report, 4 years later, our paper is accepted in the backlogs of communications and algebra and analysis and geometry. Presumably, it's not going to stay there forever, and it will one day appear. More seriously, if you're interested in learning about some systolic geometry, for instance, you think that some of the stuff you've been doing with the arithmetic lattices might have interesting applications, and you want to know what sort of questions do these differential geometers care about, then the absolute best place to go is Misha Katz's book, Systolic Geometry and Topology. So I'll end there. Thank you very much.
Thank you very much. Are there any questions or comments?
Yes, he went case by case, and he found a bound in each of the cases. I think that the idea for these bounds is if you take anything larger, you can find a counterexample, which you have to explicitly construct. And I think that's what he did for each of the cases. But like I said, the fact that in SL2R, his constant differs, I don't know, it gives me pause, is maybe all I want to say. Yeah. Yes.
What's known about C of n in Gromov?
I'm actually not sure. I think, I mean, maybe not a non-answer. I want to refer you to the book. It's called the systolic ratio. We're very closely related to it. And it's something that there are many papers on. I don't know of any explicit sort of uniform constant C of n.
But do we know if it behaves like 1/n squared, or 1 over the dimension? So it seems in your constants that they behave like the inverse of the dimension of the space, right?
Yeah,
So,
I'm not sure when you leave the arithmetic world what really happens to the constants. Yeah, I'm sorry, I haven't thought very much about those constants other than, I don't know, it is some constant which typically is going to depend on just the base manifold.
okay. But even in the arithmetic case, do you think this is always of that form, like constant over dimension?
I suspect that yes. In the arithmetic case, it's always going to be a constant divided by some simple polynomial in the dimension.
Thank you.
Yeah.
To which extent do your methods or others work for higher dimensional systems?
Maybe, well, I'm not sure the extent to which mine does, but I'm gonna get a non-answer. I'm gonna recommend that, I think Misha Belolipetsky is giving a talk. I'm not sure if it's about his paper about k-dimensional systems, but that's something that I have not studied and he has. And so I'd recommend that he's probably the person to ask.
So to get the bounds that you showed us, you basically constructed in type A some special elements with big trays. And then you said that for other types, you used embeddings.
Yes.
But it seems to me that it should be possible to just do a similar construction for other types. Is it really much more difficult, and that's the reason why it wasn't done?
You know, I have to admit, I think this is a case of if you have a hammer, everything you look at is a nail. So I've been working with central simple algebras, since the beginning of grad school. And so that is literally the first thing that I'm going to try to do, even if it's much harder than looking at them directly. I suspect that, for the hyperbolic, real, complex, and quaternionic hyperbolic, no, you're absolutely right. You don't have to go through all of this rigmarole. You can just do it directly.
Okay, thanks.
Yeah.
Are there any questions or comments? If not, let's thank the speaker again.